Hello everyone and welcome to this tutorial about computer vision. This is part 2 of building a refereeing system for saber fencing. So let's see what we have to do today. We'll be building an OCR for digits. This is inspired by this answer on Stack Flow. I will link it in the description below. I'm importing the same things like last time, but I'm adding some machine learning classifier and a grid search object. This is all from the I'm opening the video in here. It's all explained in the previous part, so let me execute that. You will notice this time I'm using the 180 version of the video, not 720p. So I'm going for higher resolution basically. This is all also from the previous part. We're using matplotlib to display frames from the video, and we can slide and we can see the images changing as we slide through the video. Because I did not run the frame basically. Sorry, I was sliding and it wasn't moving because I restarted the kernel and I did not run the frame. So if we slide now, it should, yeah, there, and the players are moving. Sorry for that little glitch. Instead of using this interface that's really limited to some degree, I'll be using OpenCV, which is a much interesting interface to do that. First, I will be reading one frame from the video. Then, instead of showing it in matplotlib, I'm using OpenCV that I am show, and this function takes a window name and a mat object, which is an image. So I'm naming the window saber fencing, and I'm passing the image that we just read from the video. Then I'm waiting for a keyboard input, and the parameter in here is the delay in milliseconds, but if we use 0, it will just wait for a keystroke forever. Then after we hit anything on the keyboard, it will close all windows using a destroy all windows method. So if we run this cell, we will get this nice window where we can zoom in, zoom out. But the thing about this window, we cannot resize it, and the image is much bigger than our screen, and if we cannot zoom out a little bit, that will be a problem. So to deal with that, we'll be using normal window to tell Python that, or to tell OpenCV that you want a normal window. You'll have to define your window first using named window method, name your window, and pass cv2.window normal, which will tell OpenCV that you want a normal window instead of an auto size window. Then I'm showing the image in the same window name that I used here. I'm waiting for a key, then close. And if we check it now, we have this nice resizable screen that we can zoom in, zoom out, and that's you can make the screen, you can maximize the screen. And one of the most interesting thing about the OpenCV interface is you can zoom in and actually see the red, green, blue values of each pixel. That will that would be one of my favorite features of their interface. The other option is to use full screen, and to do that you have to define your window, then set property, set window property of your window, and you'll pass property full screen and CV full screen, window full screen. Then you can display your image normally and wait for a key and destroy all windows, and that's how a full screen works. Then we'll be building a work interface. It's a very long code. It does a lot of things that you will need during any work with computer vision, or most work with computer vision, but it's a very helpful interface that I would modify for each very specific project, but usually the main idea remains the same. So let's run that and see how it looks. I will be minimizing my window to see that, and that's our main preview window. And we have an HSV histogram and BGR histogram. These are the two color schemas that we care about. We can slide in here to see different frames of the video. We have a BGR and HSV, so we can switch between the two color schemas. And HSV maps to the same colors, so blue for H, green for S, and red for V. The last one in here, we'll explain it in a minute. I just have to explain to you what are these limits first in on the histogram. Since we're looking at an HSV image, we can change our limits on the value. We care about reading these numbers in here, and the one thing you'll notice about this area, the value, which is the red one, is 255, and it's almost consistent throughout the number. So we can filter out everything in the image except areas with high value. So if I switch from image to threshold, I can see that I'm only getting the text around here, and as I slide this filter more and more, I will get a cleaner image of the score. I'm getting here to 244, and I'm getting a really clean image. You can do the same thing. You can filter with red, green, blue, or HSV, hue, saturation, and value, and you can just switch between them, basically. And that's the first thing we need to do. Yeah, I will run that interface once more. And actually, before I do that, I will just rerun this region of interest list. So I'll reset my region of interest list, and I will be one of the things this screen does, it can store where did you click your mouse, basically. So I will be clicking top left on the area where the score might show up, basically. So I'm telling I'm storing this point and this point, the top left and the right bottom, for the left player score, and for the right player score I will be doing the same. Top left, bottom right, and I don't think the score will go outside this area. So if we go out now, I know our regions of interests are stored. So let's start building the OCR. I built this little training set in GIMP. It's like a Photoshop thing software. I basically wrote some numbers. I sized them up and down to different levels to get different quality of the image. Some processing of the image. I'm changing the image from BGR to grayscale first. So this is the grayscale version of the image. Then I'm using comparing the fixed threshold to the adaptive threshold. So this is what I get with the fixed one, and this is what I get with the I actually have to run these cells. So this is the fixed one, and this is the adaptive threshold. Then I wanted to find the digits. I could have manually put their locations, but that will be really hard to do once you're dealing with multiple digits on a video that things might move around, so you cannot do it this way, and you might cut them a little differently, and that will ruin detection accuracy. So I'm finding contour for this image, and I'm filtering out all the smaller contours. So for example, I'm sure it detected the area inside 6 as a contour. I'm not interested in that. It detected 2 in here, 1 more in here, 1 inside the 0, and a bunch of other things. I'm not interested in these. So I filtered all the smaller contours, and I made sure that it only detected 60 boxes, and they cover all 60 numbers we have in our training set. I'm checking here a single digit just to make sure I get the digit correctly, and I'm changing the interpolation in here to nearest. This helps with visualizing each specific pixel to its value. If I remove this, it will just look really bad, basically. So this is why we use nearest when we are really looking at each pixel value. After that, I labeled all the digits to some level manually. So I went row by row. So this row had 9, 8, 7, 6, 5, 4, 3, 2, 0, 1. So, and I wrote that, and I did that for all the other rows. And this is my training set results, basically, or the Y in the training set, what we're predicting. So the area that we're capturing is a little big. It might be like 48 pixels by 24, or sorry, 38 by 24, something like this, and it's really large. So I'm resizing my image to 10 by 14, and this will help create less features to make detection basically work better. So let's do that, and this is our image now. Then I'm preparing all features, basically. So we have 60 rows, and each one of them has 140 features, which is 10 by 14, basically. training a classifier. I'm training KNN classifier in here. I'm using grid search to find the best parameter for a number of neighbors, and it tells me one neighbor is the best value for a number of neighbors parameter in here. And I'm just testing again on the same training set. I know this is a big no once you're dealing with machine learning, but it's just an indication to tell me if a classifier is at least working. So if I get 100% in here, I know it works at least. I'm also timing the prediction, and predicting 60 values takes 1.49 milliseconds, which is really good, but not super cool, but it's good enough for this application. And after that, I'm doing the same with support vector machine classifier, and you can notice the performance is faster in here. I'm getting the same 100% accuracy. And in here, I'm training a random forest classifier, which I did not really get good results from. I'm getting 80% from that. So I will not be retraining it right now. Running the classifier on video, so I will be retrieving my region of interest list, the one we clicked on the screen, if you remember earlier. So I'm just retrieving my list, and you can see that I'm splitting these points into left player score ROI and right player score ROI. I'm just displaying that just to visualize my selection. They're not the same size, but it doesn't matter because we can still get good results out of that, and it will automatically detect where our digits are. So let's do that. We'll be doing some pre-processing, so I'm converting that into grayscale using the HSV color schema and getting only the V out of the HSV. So I'm just returning the value, which is the third channel of this color schema. And this is how it looks for the left player, and this is how it looks for the right player. Then I'm doing some thresholding basically at 230 just to clean out anything else, and I'm finding the contour for this little image, and then I'm trying to draw a box around it just to make sure I get the right digit in here. So let's work on the prediction. If we just run this script, it's basically doing everything that we did before, but it's making it into functions basically, and it's reading basically the score. So I'm getting the score for the left player and the right player, and at the current screen, at the current frame, they're both 0. If we go up and change the frame, if we go up and change the frame, 1 second. Actually, let's not do that right now. But basically, if you change the frame and run this again, you will get. In fact, let's do it. let's yeah, okay. If we go in here and scroll down, for example, to here, it's 2 2. No, let's do something more interesting. Yeah, 4 4. Huh, head rows. Okay, 2 3. 3 4. And we close that and go back to our prediction and run it again. It will tell us the score is for the left player. It's 3. This is right player because I'm getting the right player. Alright. And we can see that it's reading off the score of the screen using this OCR that we just built. To do it for the complete video, I built this, I wrote this little code in here, but it takes fairly long amount of time. I cannot really do that during the video because it will be just too long and the video is already running too long. But I visualized that before, and this is how it looks. You can see the left player is red and right player is green, and you can see how did the left player basically win, and when did he score each of his points. So we can split the video later and we can analyze what happened before that, so the judge called a point for that player. And here I did the same, but I divided by frame per second, so it's in time, in seconds instead of frame, and you will just basically see the same image. I put everything in a data frame and I saved my work to a comma separated value file, so we can continue that in the next part of this tutorial. This tutorial is available open source on GitHub and it's viewable on MB Viewer. Feel free to use this or any part of it for any computer vision work you're doing. I hope if you like this, you will subscribe to this channel, and you can watch the previous part of this series by clicking here, or the next part by clicking here. Thank you.